Okay, so now again, we've wrapped up time dependence in terms of the Heisenberg picture, and hopefully all of that information equips you in your reading papers, going to talks. Whenever you see anyone talking about time evolution, it's always done in the Heisenberg way. They'll talk about, sometimes they'll just show, oh, here's our calculation of the spectra, and you'll notice that the operators have a T in them. Now you know what's happening. And one of the things that's of value to that is, when you see that, you're like, oh yeah, that's a time-evolving Heisenberg. I did that for x of t. It allows you to not get stuck on that. You know, again, you're at a presentation, you're trying to hopefully absorb some of this, and you see something unfamiliar at the top, you're not going to absorb the bottom. But that's the point. So part of this is when you see things you're comfortable with, even if you don't fully follow it, the more you're comfortable with it, the more you can digest what you see. So if anything, I hope that that's part of the value. With that said, so as I mentioned, harmonic oscillator, and I spelled harmonic oscillator correct this time. Everything is done with the creation and annihilation operators, also called ladder operators. And these are not adjoints. So you got A and A. It gets a little, it's like a dagger. It's like a little dagger in the book, and so it's not an adjoint. So you got to be real careful of that. I think it is Hermitian though, so these operators are not adjoint of each other. I got to look that up. I'm pretty sure about that. But here, I got that bigger. They're composed of X and P, and X and P are operators for things that are real and measurable, position and speed, or things that are real. So that they have to be Hermitian, and that means that A is its own adjoint, and A star, unfortunately, I am having to write that with the symbol implying it's the adjoint of A, which it is not. It's a different operator. And that is important later. Part of the derivation I'm going to do today, you have to note that they are not adjoint. Anyway, so that just bothered me a bit. Okay, so we have these two guys, and now we've got to figure out what they do. And what the first thing we did was we always, when you multiply operators, you have new operators. I mean, it's kind of brainless at this point. And we figured out that when you work multiply these out, what you ended up with was the Hamiltonian for the harmonic oscillator. And we end up with this minus a half, and therefore n plus 1/2. And so, cool. So at this point, I think we're just kind of playing tricks with operators. We have these new operators. What the hell are they? Here's a neat trick you can do with them. You can write the Hamiltonian out, and you can see basically the eigenvalue. The quantum number plus a half, which we get from just looking at by writing the double differential equation for a harmonic oscillator, finding a 17th century math textbook that gives the answer already, and you see the wave functions as we know them, and you see the eigenvalue, and that's the eigenvalue. We know that to be true. So here's a clever way of doing that with these other operators. Now, again, you will always see any talk that has quantum mechanics that involves vibration. That will be about half of those said talks. You will see them done this way every time. So it delineates people with a proper physical chemistry background from those who don't. Now I'm going to show you what they're useful for, but before I do that, I'm going to run through some of the proofs in the book. And so I'm a little hairy today because I found, so we're going to say that the states are just n, the states of a harmonic oscillator. Anyway, I was going to say I found that when I was reviewing for class, I found mistakes. And I realized they were mistakes in my notes. I realized those were mistakes in the book. So I looked at the one that maybe you found somewhere, and they had been corrected. But it's like I lost an hour because I had to figure that out. So I'm going to be a little bit meh today. So let's, okay, so the expectation value, let's call it n. So obviously this is a vibrational state. N equals 0 will be the ground state. 1 is the first excited state. You know what that looks like. This operator, which clearly returns the quantum number, it returns 0 for the ground state. I mean, I'm kind of jumping ahead, but we know what it's going to do already. And of course, this is an expectation value, so it's just returning a number. Okay. Now, what I want to prove is that this number will be greater than 0, greater than or equal to 0. And, okay, the way to do that is to have, now I already mentioned that if A plus, which is, A plus, is that creation? Which one's creation? I already forgot which. A plus is creation, and A is annihilation. Okay. I believe that they're their own adjoints because they're composed of Hermitian. They're a function of Hermitian operators. So I'm pretty sure they have to be Hermitian themselves. I think that's the case. I'm not totally sure about that, but I think that's the case. Okay. Anyway, now here's the thing. I'm not, and so. These are not unitary operators, and they are not necessarily adjoints. So this does not wipe itself out to 1. That's why I'm not using U. Right? These things have a different purpose. So remember, we got operators, Hermitian operators like Hamiltonian, momentum, position. Then we got unitary operators whose job it is to transform things into other things, transform things to move them into time, to transform things to move them into space, to rotate things. Remember one of your the last homework, that E to the I matrix, that was a rotation operator. That was a unitary operator. This is a different deal. Ladder operators are like a class among themselves. Okay, so what I'm going to say is now the eigenvalue will still be a complex conjugate of this one. So they'll be complex conjugates. And that leaves, which will be 1, which of course has to be greater than or equal to 0. Absolute value of anything has to be greater than or equal to 0. All right, so therefore, n is the absolute value of something. Which is greater than or equal to 0. And I have to admit, there's one thing about this I'm a little confused about, but I'll work it out. I'm not too sure whether those are, anyway, I'm not too sure about this. I'll have to look into this a little bit more, by the way. I know it makes sense the way you wrote it, but anyway, just warning, what I'm not sure about is that these are complex conjugates of each other. I'll talk about it some other time. I know and this is in your book, I know that, but that doesn't mean that it's right as I've rapidly been learning. Anyway, okay, let's not worry about it. All right, now the next purpose is to figure out, actually, we'll figure out what this is. What does a, oddly called the annihilation operator, do on a state? Okay, so here's the purpose, and Okay, here's the purpose. I'm going to do something I kind of hate. I always hate it when I'm in this situation. I'm going to have to do like proof, and then I combine them all. And I hate that because it's like, why are you doing this? But here we are. Well, why am I doing it? This is why. Okay, so remember that. All right, so as usual, we'll come up with, what I'm going to do is I'm going to be writing these operators as a function of commutators. And because commutators often turn into like 1 or 0, so that ends up being useful. Okay, so this ends up being a plus a, a. And remember that there are, you can always just write these out. There are some handy dandy shortcuts because they'll always turn out this way, such as this. You can take this one and put it to the left, and then you can take, of course you have to keep left and right, you have to keep that straight. Anyway, this is a handy dandy shortcut. And I'm not writing the hats, I should be writing hats on everything. It's going to drive me nuts to write a bunch of hats. And clearly that's 0. A squared minus a squared is 0. That's not too hard. Okay. Now, previously we went over this. I'm kind of cross-eyed right now. All right, when you solve this, when you write all this out, what you found is that this commutator was -1. That's actually where this thing showed up. So if you don't remember from last class, just you can just multiply the whole thing out. And you end up with like a 1 over IH commutator XP, which is IH. It wasn't too bad. It's just like everything. I hope that you find this kind of rare that we run into any kind of mathematical expression that's mind-blowing. It's usually just pages of algebra, which sucks, but is also middle school skill. Okay, anyway. All right, so that makes this, commutator, minus. Okay, that makes that minus A. Okay, then N with A plus, creation operator. That is going to end up, let me just cut to the chase here. And again, you can write this no, plus minus. Sorry. Anyway, sorry about that. So A plus sorry, that A bothers me. There we go. A on the outside. Okay, again, it's just a little right. You can figure it out that this is correct, or just write out the expression as you should. Again, this is 0. 0 is too small anyway, it's gone, it's obvious. Okay, if this is -1, then remember when you permute a commutator, then it's going to be minus itself. So minus 1 is +1. Yeah, that's right. Okay. Anyway, and then I got one more. Do I want to put this? Okay, I'll put this here. No. Tell you what. Let me start a new board. Okay. All right. As we slowly figure out what these things do, let's figure out what this is. Okay. I have to admit, I've just suddenly been blind. Let's see. Let's operate on this. Okay. Okay, let's see here. All right, why did I just do this? NA plus minus A plus N plus A plus N is NA plus, right? Oh, okay. All right, you see what I did there? All right. Okay, now let me wipe that out. So sometimes I see something like this to this, and I'm like, what the hell? It's actually it's stupid easy, right? Now, I've already done the commutator of this, so this is A plus. Okay, so this is equal to, okay, and remember, always keep your order straight. You imply extra knowledge that you may not have if you change the order. Now, by that I mean, I could have put this to the left and this to the right, but instead I kept this to the left and that to the right. Right there, I have to move this to the left anyway, and that's important because we've already seen what this does. This gives me an eigenvalue. It has a little head, right? Okay, so now we see what the creation operator does. It will, it does something such that the number operator, that remember n's job is to give you the quantum number, we figured that out already. A plus gives me a quantum number plus 1. Okay, now I'm not saying what it does to the ket, because I haven't done anything with it, but I do know that when I act on the ket, the number operator is going to give me, it's going to report that the state is 1 unit higher. Okay, now we can then do the same game with this, and again, I'm not writing the little hats because they're so freaking many, it would drive me nuts. Okay, and same deal. And we see that that is NA minus AN, okay, plus AN. Okay, let's have it operating on the ket. Okay, this is minus 1. We've done that up there. I told you you had to do a bunch of operations. So we'll call it minus 1. No, capital N, it's different. I don't know why someone did that. Okay. Let me look at my notes here because now I'm lost. This will be no, minus A. What the hell is wrong with me? Minus A. Right? So I'm going to write an A, and I'm going to have N minus 1. N minus 1. Which is equal to n plus 1, which is n minus 1. Okay. So we see, for symmetry's sake, let me write that as, I can, 1 plus n is n plus 1, all right? That I can switch around, because they're numbers. 2 plus 3 is 3 plus 2, right? Anyway, I should have planned ahead a little better though. All right, anyway. Okay. Let's see here. And then what we can do with this is figure out that the A operator acting on N has got to give some kind of constant. Operators are going to do that. It has to, and that's because n times n minus 1 okay, so for n to operate on something in return a value of n minus 1, the state has to be n minus 1, right? That's logical. And then a plus and likewise that. Yeah, okay, so there you go. So ladder operators, creation and annihilation operators. So now we see what they do. Okay, last job is figure out what the constants are. They're not the same. That's why I put that one, I gave that one a little dash. Okay, to do that, let's go back to n is again expectation value. Let's see here. Let's see, I'm grouping them. You know, I have to admit, I'm still getting a little confused here. I think it could be my notes again, because I swear, sorry, I need to look this up. I'm really screwing this up. All right, let me just show you what I have in my notes here. Okay, we already know that this is a constant. And it returns n minus 1. Okay, what slays me here is, again, my notes from the older version of the book is doing this. It's calling that the adjoint of that. I don't think it is. Wait a minute, or is it? Is it? How do you know what an adjoint? So remember, adjoints, how do you know if it's an adjoint? So adjoints for unitary operators are always really easy to figure out. The adjoint is 1 over the other operator, because when you multiply the two operators, you get 1. Right? Unitary operators change bases from no time to time, or they rotate things if we're talking about spin. They can translate things because their translation operators is unitary. And so those are easy to figure out. I'm just trying to remember, is there, you always say that there's a dual correspondence. So you know what slays me here? And again, I'm sorry I'm being so wishy-washy. I only realized like an hour before class that I was confused about this, and unfortunately I still am confused. I had convinced myself they're not adjoints. Maybe they are. The way I convinced myself they weren't adjoints was that the operator doesn't cancel out. A plus A is not 1. It's not the number 1. Besides, it's like the number operator. It doesn't spit out a 1. If these cancel each other out, then this isn't an operator at all. However, only unitary operators cancel each other out. It doesn't have to be a unitary operator. Adjoints don't have to cancel each other out if you put them next to each other. And remember, an adjoint simply just works on a bra. That's its job, just to work on a bra. This thing works on a kit, this works on a bra, and they may or may not necessarily be the same thing. Now the thing is, I did say, what did I say earlier? I did say that they're composed of Hermitian operators. So if that's annihilation and this is the adjoint of annihilation, then this would be correct, but, oh, no, but that's not necessarily the N operator. Okay, anyway, so look, I'll have to look into it, but my guess is that actually creation and annihilation are adjoints of each other. And what's confusing me is how to know that, because I think I even introduced this concept when I first started talking about adjoints. To my credit, I said it is not clear how to solve for the adjoint of an operator. If it's Hermitian, it's automatically its own adjoint. But if it's not Hermitian, then you have to use some kind of trick. Now, in unitary operators, the trick was easy. You make sure that the two wipe each other out and equal 1. In this case, I'm not sure how to know. What I want to do is to figure out how to write this operator and figure out what its adjoint is and show that it's that this is annihilation and it's creation. Anyway, all right, so I'll work on that for next class. So I'm sorry, I'm out of it. Okay, but now let's take it for granted that creation is the adjoint of annihilation. So if creation works on a bra, it will do what annihilation does on a ket, which is to drive the bra down. And of course, as any adjoint does, it gives the same eigenvalue, just the complex conjugate thereof. And you know, what's making me think of, it's making me think I need to work with these and show that that exists. To work on, to work with those two operators and show that they have the properties of adjoints. So maybe I'll do that on my own and I'll show you that they're adjoints. Anyway, so sorry, I know I've been gone off this crazy tangent. Anyway, so let's accept that they're adjoint. And so this annihilation drives it down. Creation, but acting as an adjoint on a bra will also, you know, they basically do the opposite of what they normally do. So anyway, sorry about that. I'll figure this out. Can't believe I'm so confused. Anyway, okay. So now what? Now I think we lost where I'm at. Okay, so this is going to be the absolute value, the constant squared, and then of course I've got n minus 1. And always I assume that everything is normalized. And actually, I already wrote this, right? Okay, so therefore, what you learn from all of this is that A, operating on n, the constant is square root of n. All right, so you see that? Expectation value, which is equal to 0 or greater. It's simply not negative. By definition is the expectation value. So, I mean, there's nothing to prove here. This is like a definition. If the creation is the adjoint of annihilation, which is the thing I just blabbered about for 20 minutes, if that's true, then of course it returns the absolute value of something squared. And so of course any one of these values is simply the square root of that. And we already know that A operating on a state drives that state 1 unit down. It drives, you know, the first decided state becomes the ground state. And the constant, for all the reasons I just said, is the square root of the original state, the quantum number. Okay. And tell you what, by the same rigmarole, let me not do all the same damn thing for what, for all my obvious confusion. Let me just say, if you do through that same rigmarole for creation, you get the square root of n plus 1, and you drive the state to one excited state higher. Okay. And then the last bit. The last bit about this is to note that n is an integer. I have to admit, I gotta look at the book more closely. I'm wondering if I'm not confused. I'm wondering if I'm confused because I just didn't look at the book closely enough. I mean, I know the book is very confusing, but I have had this class before. It's like reading through something twice. It's always easier. Then I'm kind of immersed in this stuff anyway, so I never forgot it. Okay. Now this part did confuse me. Now I'm realizing I'm even more confused. If you apply annihilation, the way the book puts this, I have to admit, this confused me. Now obviously I'm more confused than I realized. But anyway, if you apply the operator over and over and over and over and over again. Okay, so we know that, let's see, what does it do? It gives the square root of the quantum number. And then it would give, God, what would it do? See, it would be like, let's write this down. Oh, and minus 1, right? So I don't know how many times, whatever k is, n minus k, I guess. Okay, it turns out this would be equal to the square root of k minus 1. So if you factor it, if you factor all this stuff, that's what you're going to find. Okay. So again, the end state was driven down k times by the application of the annihilation operator k times. What is a little bit hard to follow along, I found it a little hard to follow along, was how the eigenvalue turns into k times k minus 1, k minus 2, yada, yada, yada. Okay. Now, you know k is, okay, so you're assuming k is an integer, right? I'm not going to apply an operator 0.5 times. What? That doesn't make any sense. Okay. So what happens is, if k is not, if k or n is not an integer, what we have is that this could be a negative number. So, long story. Again, I don't fully understand this. I just kind of accept it. I'm sure if I maybe plugged in numbers in the calculator, it would just, if I did enough examples, something like that. I don't like, that's not a rigorous proof, but anyway. If n is not a number, an integer, because k is an integer, if n was not an integer, you would find a situation where you can spit out a negative number here, but we've already proven that n has to be greater than or equal to 0. So remember when we did expectation value, n, yeah, right here, we did it right here. So again, if n is not an integer, I never said what n was. Well, I said it was a quantum number, so it has to be an integer. Anyway, if n was not an integer, then multiple applications of the annihilation operator can give you a negative number. And that would violate this. So again, if n is not an integer, therefore, n is an integer. And as we've already said, from here, from the expectation value, again, using, remember when I first started babbling about this, I said, no, wait a minute, I'm not sure if these are the same number, because that means they have to be adjoints of each other. So anyway, so you see me really get cross-eyed today, worse than I ever had, to my knowledge. Anyway, so it has to be 0, 1, 2, 3. Again, I'm kind of preaching to the choir because, I mean, you've had Harmonic Oscillator as an undergrad, and I know you saw Harmonic Oscillator as an undergrad. We were there. But anyway, so maybe 5 more minutes? Okay, because I know we talked. You're okay? Fine. Okay, and anyway, the video will still be the normal 45 minutes. Okay, so now the take-home of all of this is that, you know, the quantum numbers of harmonic oscillator, which go into the energy, n plus 1/2 HW, those are whole numbers, 0, 1, 2, 3. We already knew that. You don't have to solve the harmonic oscillator this way. You certainly seldom do it as undergrad. You just show the differential equation and just stipulate that some old geezer back in 1750 solved it. And that was the result. And what I also do with my undergrads is I always have them do the ground state, plug it into the Hamiltonian, sometimes the first excited state, and you show that it works. And now again, that's not a rigorous proof because you technically would have to show that for every state. There's an infinite number of states, but and then mathematicians have clever ways of resolving issues like that. Like I showed you how to show that relation, the homoblast, right? That if the derivatives of two functions that look completely different, but if their derivatives are the same, then they are the same. I thought that was clever. I'd never seen that before. Okay, anyway, let me tell you what's real important. So for now, we've played a bunch of tricks and proved things about the harmonic oscillator we already knew. The value is you will see these operators forever. Well, and maybe even after you're dead, I don't know. But here's where they're really useful, and this is why you see them. I can solve for x, right? So I just erase them. Okay, one was x plus IP, the other one was x minus IP, constants, whatever, right? Okay, so it turns out that you can do this. I shouldn't have done that. I mean, you can figure this out very quickly. Oh, and momentum. That's an I, by the way. That's usually MW, not WM. Want to be conventional. Okay. So that ends up being absolutely hideous. No, hideous. You would not believe how useful this is. This is shockingly useful. All right, so let's go ahead and start solving some problems with it. Okay, if you did this, let's figure this out. Let's see. Let's have A operate on the right, which is more normal, so that would give square root of n. We've got n prime n minus 1. Now, you know, of course, to solve that, you would resolve an identity with x, and then what you'd have is the complex conjugate of the first excited state times the regular wave function of the ground state. What happens when you integrate two eigenfunctions, but they're not the same? What do you get? If you integrate the same eigenfunction squared, you get the number 1 because they're normalized. If you integrate two eigenfunctions, but they're not the same eigenfunction, 0, right? Orthonormality. So this is square root of n. Now, you might think I was going to call it 0. No. It's the Kronecker delta. I never said what n prime was. So this has got to be n minus 1, in other words. If not, it's 0. Okay, and then likewise, now I know you're probably looking at this like, well, what the hell would I do with this? So this would be n plus 1, n prime, creation subtracts 1, I'm sorry, annihilation subtracts 1, creation adds 1. Delta. Okay, so the point is that if you're evaluating position or momentum, and you've got it as a function of these creation and annihilation operators, you have a problem that you see that it's kind of basically be 0 all the time. Okay, so let's figure out, now remember when I do an expectation value for position, I need to be plugging in a state. Now if I wrote this, let's do the ground state. N equals 0 is the ground state. What is it? Same state, right and left. That is what in expectation values are always defined as, you pick a state that appears left and right and the operators in between. Given what I've just shown you, these operators, if they have the same state left and right, what do you get? Huh? Okay, but now evaluate it. 1. Okay, if these are the same state, if n prime is equal to n, you get what? 0. Right? This state has to be 1 minus that state. So if this is the first excited state, then this has to be the ground state. And this one, if this is the ground state, that has to be the first excited state. Right? Because annihilation knocks you down 1. And then the overlap of two different states is 0. Unless this state is that state. So in other words, if this is the first excited state, that has to be the ground. If this is the first excited state, that's the ground state. Why? Because this takes the first excited state and makes it the ground state. Then I've got ground state, which is 1. Right? Yeah. Here, this is the ground state, that's the first excited state. Why? Because the creation operator takes the ground state, turns it to the first excited state, and then I need first excited state to get 1. Any state overlapping itself is 1. Okay, so again, with the same state left and right, what's the average x? Okay, and it's not going to be too hard to figure out what this is. Also 0. Of course. Yeah. They're the same, A plus A minus whatever. Okay. Now we're going to solve the wave functions next time, but we already know what they are. That's the ground state. What's the average x?
0.
Yes, it's 0. It's centered and even. Now, if the momentum, now remember that this is we can think of it as a bond, but you can also think of it as a particle trapped in a harmonic well. If the momentum, if the expectation value of momentum was positive or negative, if it was positive, this particle eventually goes away. If it was negative, it would walk to the left. Eventually it would reach the other edge of the universe at some point. Does that make sense? No. So What happens is, once it's gone too far to the right, it goes back to the left. And on average, those cancel out, so the momentum is zero. It's trapped. The potential traps it. Okay, so the point of this is you can start taking some kind of painful problems and solve them real easily because of this relationship. All kinds of hard problems can be put into the creation and annihilation operators, which can be evaluated in your head without Mathematica and all that jazz. Okay, last one. Let me just do this one real quick. Let's just give another practical example. Let's take FTIR. Right, FTIR spectroscopy, and you got all kinds of peaks for vibrational, this or that. And you know that any one peak is, of course, ground state, absorbing light to the first excited state. And that's okay. A HCl, say this is HCl, absorbs infrared light and goes from the ground vibrational state to the first excited state, right? Again, high school maybe, definitely freshman chemistry, you learn this stuff. Okay. You know that the strength of the transition is proportional to the dipole operator. So what the Beer's law coefficient basically, how strong the absorption is based on the dipole operator. The dipole operator is basically just minus E coulombs, and let's call that bond. Let's say that's in the x direction. Dipoles are charge times distance. Okay. So the strength. Sorry, I should have done this way. The strength of the transition is based on the expectation value of the dipole operator, and the dipole is, of course, charge times distance. Okay. Can we get something transitioning from the ground state to the ground state? Because that's exactly this same problem. Okay, notice that that's also a stupid question. How could you absorb energy and not do anything with it? That's impossible. It violates conservation of energy. Okay, so we got that going for us. But that, it should do that, right? You can't absorb energy and stay in the same state. You have to do something with it. So, and there's this, and there's this. They say the same thing. It makes sense. Okay, can we go from the ground state to the, okay, I have to think about this. First excited state. Okay, here we go. Could we go from the ground state to the second excited state? Could we do that?
Yeah.
Okay, now on the right, take the constant out. Okay. Based on this, does that work? So the excited state either has to be one below the ground state, which is not ever true. That's impossible. or it has to be one above the ground state.
What's on that?
Right? It's,
What's on that?
so, based on the harmonic thing, all absorptions in an infrared spectrum are from ground to first excited state. Right? Because every other transition is not allowed. Because that's your operator, and that SOB doesn't allow anything except going up or down one. Or the matrix element 0.
The dipole operator.
The dipole operator being x is 0. Okay, now what about, let's say that you use a laser to prepare to put, you call this pump, you pump something into the first excited state. Could you go from the first excited state to the second excited state?
How we,
Yes, you could. What you could do is you hit it with an infrared laser to go from ground to first, and then you could do an infrared spectrum of what is left over. You blast HCl gas with the right wavelength, and you use a laser to blast the living hell out of it. Get them all in the first excited state, and then do an infrared spectrum. And where's your absorption? From here to here, right? Now, would that energy difference would technically be the same. It would appear at the same spot, right? Because delta E would be okay, so to go from ground to first excited state, or first excited state to second excited state, so it doesn't matter what n is. The change in energy, which is the spectroscopic wavelength, if I subtract those two, n disappears. It just ends up being, right? If I subtract those two, it's just h bar w.
Psst.